All right, so let's start. Today, we will talk about many light methods. So far, we have seen how in participating media, in the last lecture, we saw how in participating media, we perform volumetric path tracing. You might have also seen in other lectures, photon mapping. And in previous lectures, you also talked about, you might also have seen how instant radiosity works. So in this lecture, what we will the main motivation will be to understand how the most complicated scenes with a lot of light sources, for example, the one you see in front of you, can be rendered. So in this scene alone, there are more than 360,000 light sources. The scene complexity in real life is really very high. So, for example, this football stadium in Lyon in France, as you can imagine, the amount of light sources and illumination, which if you want to render it in a virtual scene, could be really challenging. Similarly, in any aesthetical place, you could see the chandeliers. These things could be really complicated to render. And also in our lecture halls, we have many lights there, and we would like to find a way to render these things more efficiently. All right, so with this motivation, today we will cover briefly again instant radiosity, which is said to be the birth of virtual point lights. And then we will also see how we can move from point lights to more non-point lights. Like, for example, we will look at one instance of that, which is virtual ray lights. And in the second half, we will see how we can accelerate the computation of illumination using virtual point lights as such, using LightCuts in their stochastic versions. And in the end, we will also see a more fast version of rendering explosions. All right. We saw in previous lectures that the way path tracing works is that you shoot a path, and the idea is to stop this path when the light hits. There was also a bidirectional version of that where the light path is also shot, and then we connect the paths of the camera ray versus to the light versus. This is how the bidirectional path tracing works. Now, instant radiosity kind of inspired from the way bidirectional path tracing works. So the idea is that we kind of extends bidirectional path tracing in instant radiosity to generate virtual point light sources. So the idea is rather simple. You have a light source, you have a given scene, you shoot your path, and for each vertex of your path, you convert that path path vertex to a point light source. And at that point light source, at that vertex, you keep the underlying BRDF properties. Like, actually the full throughput of the path is kept at a given vertex depth. So at each depth, as the path is traveling, the flux of the light and the underlying BRDF multiplication represents the intensity of the light there. And once you have generated virtual paths, virtual point lights, the next step is to light your scene. So for example, if you want to render this particular point, what you would do is you would connect to all the VPLs available in your scene. So in summary, there are two aspects of this algorithm. First, you generate the VPLs, and the second is you find a way to render your scene using these VPLs only. Now, this could be really challenging. And first of all, like, if you want to generate VPLs, we would like to find a way to do this efficiently, because there could be scenes which are not visible by even the virtual point lights, where the path cannot reach. And in the lighting also, we don't want to connect to all the VPLs. So let's first look at how to efficiently generate the VPLs. Before I go further, If you don't hear anything properly, or if you feel like I'm going a bit fast, please let me know. And also, if you don't understand anything, feel free to interrupt me. All right. So let's look at generating the VPLs. Let's consider this simple scene where we have objects which are, let's say, in a kind of a separate room at the bottom, and the light source is in the separate room. So if we generate path for a light paths and register the corresponding VPLs, you could see that for a given camera view, there might not be any VPL available. And even if you try to, let's say, render scene for this camera view, there might be only 3 VPLs you could connect to. And if you, this is how the instant radiosity, actually, this is the whole idea about instant radiosity. And if you render an image, for example, you can see the reference on the right, and on the left, you could see what goes wrong in these scenarios when you naively try to connect to the VPLs. Okay, now another problem with VPLs is that the glossy interreflections are not handled properly. So in this scene, you could see some splotches near the teapot. So if you could see my mouse cursor, or just look at around the teapot, which is touching the surface of the kitchen here, you could see the splotches there. Now, instant radiosity assumes by construction that, to simplify the light transport, they assumes that all the surfaces where you have the VPLs are diffuse. So the glossy component is removed. So if you clamp, or you could do also clamping directly. So if you clamp the energy, you would see the loss of illumination there. The glossiness is gone, but you could see the problem there. So you, of course, get rid of the splotches, but the whole illumination has changed. And you can see how different it is from the reference. Another problem with the way the VPL works is that we would need very high number of VPLs for glossy regions, because since the VPLs are generated in such a way that you also, like, once you have these virtual point lights, they are called virtual because they're not real light sources. Like what you have done is that when your light path was growing, at each vertex you have kind of stored the throughput of that, and you use that as a virtual point light source. So depending on the underlying BRDF, the glossy surfaces would have a special orientation of the underlying BRDF. So the VPLs will be concentrated in certain directions and not in other. And that could also be a problem. All right. So given this, our goal is to place VPLs where we really need them. And there were multiple approaches developed in the past to improve that. So one of the most simplest was by Ilya Georgi and Philip Slusalek in 2010, where they decided to reject unimportant VPLs. It was a short paper, so the idea was rather simple. You probabilistically reject VPLs where there is low expectation of contribution. So for example, in this scene, if you have generated the VPLs, which, as you can see, are quite dense in the region where the light source is in the room, and other places it's not really that not dense. Probabilistically, you reject all the VPLs which you are kind of somehow you probabilistically get to know that they will not contribute much to the illumination. So the approach is simple. You first estimate the average contribution of a VPL, denoted by phi of V. You shoot some pilot VPLs to illuminate the surface point seen by the camera. And then you use those pilot points to compute the average. And once you have these averages, then for all the VPLs you generate, let's say you want to estimate the ith VPL contribution, you do it by checking the probability. So you accept the VPL if the probability P of I is equals to minimum of phi over I normalized by the average VPL. and then you divide its energy by the pi. And if you recall, this is pretty much what we were doing when we spoke of Russian roulette a few lectures back. So by just doing that, the algorithms becomes more simple. This process is rather cheap to do, and thanks to that, all the VPLs have roughly equal contribution, which works well most of the time. The problem with this approach was that first of all, it increases the cost of VPL distribution because you have to kind of keep track of their energy. You first have to generate the pilot points, and then you compute the corresponding probabilities to see if you can accept or reject the corresponding VPL. The whole algorithm works under the assumption of one pixel image, which means that you generate VPLs for one pixel, let's say, and then you keep the same VPLs for the whole set of the image. And that is a problem. And last thing, like this approach, of course, is simple, is cheap. It helps generate VPLs where you really want them to be, but it still does not handle the local interreflection problem. So here is one instance where you could see the improvements of rejecting unimportant VPLs. So on the left side, if you don't do any rejection, you could see the artifacts in the shadows. You see this weird kind of bending there in the shadows, but with rejection, with the rejection approach where you have just accepted 7% of the VPLs generated, you could see that it kind of improves the overall quality. All right. The next algorithm, which does something more, I would say this is kind of is more robust than the rejection approach, is bidirectional instant radiosity by Segovia and colleagues. So their idea was rather simple. So just like in a bidirectional approach, you generate a path, and then for the camera surface, the camera path, at the second vertex, they treat that as a VPL. And they do this for all the paths. And thanks to that, they ensure that the VPL is generated where the camera could actually see it, or actually is in the vicinity of the camera, the VPLs generated ones. There was another interesting approach, which was kind of from the same set of authors. They further play with the bidirectional approach of generating the VPL at the second vertex, where instead of just generating at the second vertex, they decided to mutate the path using the metropolis approach. So by mutating the path at the second vertex, they generate VPLs which are more close to the camera in the scene. And as you could see in the middle, we have the bidirectional instant radiosity of the scene, which we saw earlier. And on the right, we have the metropolis instant radiosity. And you could see that the metropolis approach works quite well here. But the problem with this metropolis approach is that first, as it's well known that it's quite complicated to implement the metropolis approach, and it again does not help with the local interreflections. The advantages on the other side is, of course, it can handle large and difficult scenes, which we just saw, where the light source was not in the same room, and it managed to acquire the illumination pretty well. And of course, the VPLs have equal contributions there. All right. So before I move to the next part, where now we will talk about how we will perform lighting with these VPLs, are there any questions?
Yeah, I have a question. So how
I cannot
does
hear
this...
you, Eric, if you're
Oh,
speaking.
you can't hear me? Really?
Yeah, I can hear you now.
Okay, now you can hear me? Okay, perfect. So how does this differ from bidirectional path tracing, where we'd be tracing from the light and then connecting them anyways?
Right. So in bidirectional path tracing, we we just shoot a path, and then we just connect those paths, the camera paths, to the light path vertices. The only difference is that here you can restore the VPL. So you assume that you have, you kind of assume each vertex as a point light source itself. So it has an emission component there. So when you will treat this, when you will hit this light source, you can first of all treat that as a point light source, and second, you can even store this. And what people do, or what most of the algorithm does, is that they store this VPL, they generate it once and for all, and they use this VPL as it is. And that's, you will see later, that's actually caused the problem. But the observation is right. It's very, the idea is pretty much the same as bidirectional path tracing. Any other question? All right. So next part of the lecture, we will see how we can find a way to perform lighting with these VPLs. The brute force method, of course, is to use simply connect to all the VPLs, but let's see if we can do better. All right. So given a hit point, a shading point, and outgoing gradients and ingoing gradients directions, let's say on one side of the slide, we can write the radiance equation, rendering equation in an area formulation also. So here, the first term is the L on the left side is the radiance term coming from x1 to x0. The emittance, which is going from x1 to x0, and you have the integral over the areas, where f is your BRDF term, g is the geometric term, which takes care of the orientation and the material properties, like how one point interacts with the other. And the third term is the visibility term, which tells you whether the next point is even visible from the point of the query point. And then you go back to your recursion, where you have the radiance function going from x2 to x1, and the process continues. All right. If you look at the full path, we can generate a path of k vertices, and this path has their own throughput components, g and v, which g is the geometry term, v is the visibility term for each of the segment of the paths. And what VPL does, we just discussed, is that it takes the throughput of the path coming from the, let's say, the light source, and treat a particular point or vertex as the point light source. And what we want to do is once we know that, okay, this is the point light source, then we want to perform the query on the segment x1, x2, which means that we want to worry about the components g, the g x1, x2 term, and the b x1, x2 term, which connects x1 to the x2 here. All right. So once we have this equation, what we just saw on a one path, how we convert one path, full path, to a VPL version of that, we can also kind of rewrite the rendering equation in the same way. Here, the first term is the same as the BRDF, which we have seen. The second term is also pretty much the same. It's the geometric term. Here, I think the subscript I is by mistake. It should be k here. So it's just that at a particular vertex k, what is the geometric term with respect to x1? V is the visibility term. And now we have kind of hide the recursion term in the BRDF at the point x2, which is now treated as the light source, and phi term, which is the flux coming at that ith VPL, which we assume as a VPL now. So we consider both the BRDF and the flux coming there. So what happens when we perform lighting? So given any reference image, if we try to approximate the lighting by VPLs, you could see some visible problems there. So you could see the splotches, which are like really affecting the corners and the boundaries. Anybody can guess why that could be happening here? Like why it's affecting really these corners and these places which are kind of at the boundaries. Not even exactly the boundaries, it's like when surfaces are close to each other. You can make a wrong guess, that's not an issue. All right, so if I'll help you here. So like we saw that there is a geometric term involved in that, right? So the splotches are there because, and especially so where the surfaces are so close, is because the geometric term by definition has the distance square, inverse distance square term in that. And what it means is that, let's say if x1 is your VPL, or let's say x2 is your VPL, the way we formulated it, then if x1 is too close to x2, that means x1 minus x2, the distance will be very small. And that will kind of increase the overall contribution of that VPL by large magnitude. So what it means is that all the VPLs which are really close to any other surface, for example, especially here near the corners or the places where the walls are meeting, here the distance is too small, so the splotches or the VPLs will become highly illuminated there. So that's the reason here for the splotches. And this also causes singularity, which is what it is. All right, another issue with VPLs, as I mentioned, is that the idea with VPL generation is that you generate VPLs once and for all, and then you can use the same VPLs, same set of VPLs for the entirety of your rendering. This is done for the purpose of avoiding noise. Because if you use the same VPL everywhere, then there is no randomness around. And that is really good to avoid noise. But this can really affect the image, the perceptual quality of the image. And you could see some bad correlations popping in. And that's also bad. So we want to get rid of both of these problems. There are two different solutions to handle this issue. The first one in the top is that you somehow bound the geometry term. The way it is done is that once you bound it, it starts removing energy, but it's done very mechanically. So it results in darkening of the image. There is some loss of illumination, but there are some compensation terms derived to avoid this bias and get better kind of to keep the full illumination of the image. The second approach is, which we will see later on, is how to distribute the flux of a VPL, which is right now is a point, or in the mathematical term, it's kind of a Dirac. We can, if we can distribute it over an area or a volume, that could help consistently remove these singularities, and hopefully progressively the things gets better. First, let's look at how we can bound the geometry here. By geometry, I mean the geometric term, because the singularity was happening because of the inverse distance square term in the geometrical term there. All right. So the naive way to do things is you want to avoid explosion of the geometric term, which is your G of x1, x2. The easiest way to do is that you just say that, okay, I will give a constant term when I'm rendering, and I'll make sure that I will pick only the minimum of these two. So I will threshold the geometric term after a certain value. The advantage, of course, is that it's extremely simple and fast. There is nothing you really need to do. You choose your threshold. The problem is that it avoids, it removes the energy, so it darkens the image. So on this image, on the left side, you have the reference. In the middle, you have the VPL, which we just saw. And on the right, you could see what happens when we bound the G there. You can observe that if we take the difference of these two images, the reference and the corresponding bounded VPL rendered image, you see that near the boundaries, this difference image is bright, which means that there the difference is large. And in the rendered image, you could see that where there was splotches before, you could see that they are becoming dark. And that's because this thresholding is not aware of the underlying illumination. So it's done manually, so it can create problems. And we want to compensate for the loss of energy here. So the way we can compensate is there are many papers which were published to get rid of this artifact coming from bounding. So here I have written the same rendering equation in the area formulation. The T operator, you can assume here that the T operator, what it's doing is that it's just telling you, like for a given outgoing radiance, you are just adding another bounds to your path here. So this is what the meaning of having an operator T applied to the radiance function. Now, the same equation, when you apply your bounding term, let's call it T of B. And what you have done here is that you have simply changed the geometric term, and you are writing it now as minimum of you take the minimum of your threshold defined by B and the geometric term itself. So what is left? What is left is the residual term. And the residual term here is simply the maximum of the difference between the geometric term and the threshold itself. And what the next slides, which I will show, will show you how the algorithms compute this residual light transport left in the scene to kind of compensate for the illumination. Now, given this, the bounding operator and the residual operator, we can write the above light transport operator, which is applied to the radiance, as a sum of these bounded operator on the light transport and the residual operator on the light transport. What it means is that if you have an image which you just rendered using, let's say, these bounding things, what you're getting is that the estimation using your VPLs after the bounding, the T of B, and you add the residual term in that. So you need to kind of know how to estimate this residual term. We know how to estimate the VPL term, which gives you this darkening, but we also now want to find a way to estimate this residual there. So the question is, how do we compute this residual transport? There was this nice algorithm proposed by Colligan and Keller, which was later extended also to participating media by Hub et al. Was that, let's imagine that you have, you perform your VPL generation, and then now you want to compute the lighting at a point x1 here. So the idea is that, of course, you will connect it to all the VPLs which are visible, or let's say a set of VPLs, maybe a smart way to connect to the VPLs. And now if you see the blue arrows there, these are the ones which have bounded contributions. What you want to do is you want to somehow get back the illumination which was lost when these blue arrows were bounded. Now, this is our region which is bounded. So what they proposed, Colligan and Keller, they said that, okay, we will shoot array. So what they did is they tried to compute this TR term, which is the residual transport, which means that from x1, you shoot a path. And if that path vertex lies again in the bounded region, which means that when you will connect it to the vertices, it's very possible that it will be clamped again because of the bounding operator. You would continue computing this path till you are out of this region, which has the bounded contribution. And then you will take the contribution of this path and it will be added to the x1 vertex itself. This was working. This was a simple idea which was helping recover all the energy which was missing due to the bounding thing. The algorithm is unbiased, which is good. But the problem is that you can easily imagine that this process can recursively becomes large, which means that your path may become really large before it gets out of the bounded contribution region. And that means it kind of becomes a path tracing after that. And as a result, the whole process becomes super expensive. So just to give you an example, recovering a 10% of energy here can take 90% of the rendering time, which might not be a good trade-off here. Oops, sorry about that. Yeah, so here where you can see what's happening is that if you just look at the two scenes, they look pretty much the same, right? On the left, you have the bounding term used only, and on the right side, you're doing the compensation. Can anybody tell where the difference is happening in these two images? It's just a visual inspection. You can.
Is it like the shadow below the chairs and table?
Well, that's might be true, but it's really difficult to spot. That there are similar regions. I mean, you're close. The way I think you're thinking, the effect should be visible in similar kind of regions, which are kind of occluded, partially occluded.
Like the window panes?
Exactly. So this is where it's more easily visible. So I think what you're saying near the chairs and the shadows, it might be happening there as well, but it's easily visible on these blinds here. So you could see that in the bound, when you were doing the bounding, you were losing this energy there, and you were getting these dark regions. But on the right side, you could see these are well compensated. All right. So there was another interesting approach developed by Novak and colleagues in 2011. So what they did is that they tried to do this compensation as a post-processing filtering in the screen space. What it means is that, for example, if you write a rendering equation, which is radiance equals to the emittance term plus the transport operator applied to the radiance, which kind of calls for the recursivity, you can separate the T of L term, which is the radiance, into a direct illumination, where T, which is T of LE, plus the indirect illumination with the L of hat. Now, the indirect illumination here can be further subdivided into the bounded operator term and the residual transport term. And here you can also write the trick they used is that they assume that the indirect illumination is not affected by the emittance term or the direct illumination term, which is what happens. So they replace the indirect illumination term in the residual transport by L minus LE. And oops, sorry about that. So what happens here is that if you do this recursively, this would actually be simply written as an approximation in this form, which is at the bottom of the equation, where what you're doing is now you're iteratively applying the transport operator and you're to the component, the direct and the indirect illumination, where the indirect illumination is bounded. And what they kind of observed is that this term can be computed only once and stored, and then you can iteratively apply the residual term on top of that. What it means is that you compute the direct plus bounded indirect elimination. For example, in this scene, and after that, you apply the corresponding residual transport, which means that you compute the next outgoing gradients from the given, you compute the next bounds at all the outgoing gradients coming at each point. And they simply add the leftmost image, in this case, to these images which are computed after applying the residual transport operators. And what they observe is that by simply doing it 2 times, like by just doing it with 2 bounces, that was sufficient. Like the 2 bounce residual was sufficient to get back to compensate for the loss of elimination. So here on one side, you have this direct and bounded indirect computed image, and the corresponding residual image after 2 bounces. And by compositing, you could observe slight change in the illumination. To really see it, the difference, look at the borders of this curtain, and also the overall curtain itself. On the left side, the curtain is slightly darkish, and on the right side, it seems properly illuminated. All right, so they also further extended this approach to volumetric medium with the participating media itself. So here they tried to render, let's say, this smoke behavior. If you use simply VPLs, the VPL approach, which means that you represent the paths which are going on. You can imagine all the scattering which is happening in the participating media, and you try to represent with the point light sources. You get these really sparkling effect, which might be looking nice, but it's actually are the singularities which are not good. And if you start bounding them the way we saw by using some kind of user-defined threshold V, then you see the darkening happening there, which is not acceptable. So what they did is that they applied the same idea of you computing the corresponding direct elimination plus the bounded indirect elimination, and then applying the residual transport over 2 bounces. If you let's look at the what's happening at the radiance at this yellow line, the scan line here, which I have drawn there over the image. This green curve is the reference illumination at this yellow line. The orange peak happens because when you compute the corresponding VPL way of doing things. So if it is a VPL computation, you will get these spikes. This blue term is the bounded term, which we compute simply by thresholding the value by B. And after adding the first residual transport, you get the red curve. And if you, after applying the second residual transport, the red curve matches closely the reference itself. So this is the way they kind of showed that the 2 bounces are sufficient to compensate for the lost illumination here, lost energy. So the idea was pretty simple. They optimize using the corresponding bias compensation there. So they compensate the bias. And one thing they assume here is that everything is kind of locally homogeneous. So we remember from last lecture, homogeneous media is something where the scattering coefficients are constant. So when they say they are assuming locally homogeneous media, it means that maybe they define a local region where everything is homogeneous. And we also saw this voxel grid approach where this kind of already assumed there. And they also don't perform any local visibility testing there. And this is like, even under these assumptions, they still manage to get a good compensation for the lost illumination there. The disadvantage of this approach is that it's of course approximate and could be complicated to implement. Okay, so this is the one of the interesting results they got. If you perform the bounded approach, this image getting the same quality took around 39 minutes. And with approximate bias compensation, which took 30 minutes, they managed to get this nice looking smoke effect in this scene. All right, so far we have seen how we can bound the geometry term. We saw how it loses the energy when we apply these user-defined thresholds. And we also saw how we can compensate for this loss of energy to make the overall result unbiased. The next we will talk about how we can distribute the VPLs over areas or volumes, which is maybe more interesting and rather more appealing and more, I would say, exciting than just bounding the terms. But yeah, before we move into that, if you have any questions, please feel free to ask. All right. I assume everything is clear so far. That's good. So the idea of using of spreading the energy, or the kind of getting rid of these singularities, or if you cannot get rid of, at least remove or reduce the effect of these singularities, is to spread the energy over a finite region. The problem, as we have seen already, why this happens is that, so on the left side you see the instant radiosity, and on the right side you see the reference. And in these circle regions, you see the loss of illumination there. This is problematic, and we want to get rid of that. We don't want to have this loss of illumination. Or let's say if you want to do the compensation by, for example, the Collick and Keller method, on the left side, the image generated was done after 3.5 hours or so. This was done by Hasan and colleagues in 2009. So the timings are reported for that like 10 years ago, the machines which they used 10 years ago. And if they use, so Hasan and colleagues are the ones who proposed this idea of using virtual spherical lights. So instead of using point lights, they proposed to use spherical lights, and you could see the change which you would expect there. You see the nice, the illumination has been well captured there. There appears to be no loss of illumination there, and you don't see any of the artifacts. One of the problems with instant radiosity is that it simplifies the full light transport equation by assuming only diffuse surfaces. That helps them simplify the full mathematical formulation and use the VPL approach. But if there is a glossy term, that could be problematic, because if you assume that at each point where, so for example, the surface on the you see the streak on the ceiling, this streak is coming up there because it is caused by a VPL which is located on a highly anisotropic glossy surface there. And the similar thing you can observe on the on the kitchen side there as well. So you want to get rid of that, but not by simplifying the scene where you actually lose all the effect. So we want to keep the corresponding the glossy component there. If you clamp this, for example, the way you want to do it, the problem is you would see there are still some splotches, which is not nice at all. So the way Hasan et al. Proposed, like, of course, they found that the problem is always the same. The problem is happening because there is a geometric term which involves the distance between the VPL, here P, and the point of illumination. And since the geometric terms clearly tells you that as the distance decreases, this term will go to infinity, which means the VPL contribution will keep increasing, which were causing the splotches. So so there were these two issues. What they did with virtual spherical lights is that they proposed to spread the energy of this Dirac VPL over a finite surface. And what they do is that they compute the corresponding contribution as a solid angle integral. Let's have a look at it more closely. So what they did is that, so in the VPL approach, what's happening is that you have two surfaces. X2 is your VPL and X1 is the surface where you want to compute the illumination. This is a point-to-point illumination. What they do is that they replace their VPL with this sphere, the visible sphere. And thanks to that, now what's happening is that in the VPL approach, they had the point-to-point radiance equation, which was computing the flux multiplied by the visibility term, multiplied by the BRDFs, f of x1 and f of x2 at the x1, x2 locations, and the geometric term. The problem which was causing the splotches was the BRDF terms, because if they are glossy, they could be problematic there. Or if you have corresponding closer surfaces, that would cause a singularity due to the geometric term. If you use the approximate sphere two-point term, which they proposed, as you can see, now the flux is normalized by the radius of the surface area of the sphere. And now the geometric term is actually replaced by the integral over the visible hemisphere, over this solid angle visible from the point x1 over this sphere. And this gets rid of this inverse distance square terms that helps remove the singularity. The benefit of this approach was that you could actually use any way to compute the overall contribution. What it means is that you can perform the sampling. For example, you can actually directly sample the solid angle, the cone sampling in the left image. Or you can actually compute it using any BR or the BRDF at the point x1. You can also perform the sampling with respect to the importance of the BRDF at the point light source location x2. And by simply MISing them, which means that you simply perform by doing the multiple importance sampling of all these techniques, you would still get a nice illumination of this. So this was really beneficial. So since there is no way of introducing the singularity, things were easy to import and sample together. The benefit of this approach is that the energy is blurred, so you don't really need to clamp. It's happening automatically thanks to the way that it is formalized. But it could introduce bias. And another problem, which is more related to the overall computation, it requires an extra integration over the solid angle. So you already have an integration happening in your rendering term, but on top of that, you also perform this integration of the solid angle, which requires another important sampling there. If we look at the improvements coming from VSL itself, on one side you see the reference, and on the other side, on the right side, you see the VSL improvement, and you could see they are pretty close to each other. And in the middle, the clamping term, even though it is fast, you could see it actually is not at all close to the reference. There is too much darkening on the floor, which is easily avoided by the VSL approach. And you could see it took like hardly a minute or so to compute that. And this is just a close-up to show you how this is behaving. Now, in the case of VSL, you could see that it's not that close to the reference, but this is the result which I chose to show, which is computed by a reasonable amount of VSLs at a reasonable time. But if you have, let's say, millions of VSLs, which you can generate, then the timing would be large, like it will take a long time to compute this, but the result will be close to the reference. This is to just show that the overall approach, even though it looks biased, it is consistent. So as you keep increasing the number of VSLs, the result will go towards the reference. Any questions so far? All right. So the next idea is to, instead of distributing light over a sphere, is instead of we kind of distribute energy over a ray. So that was the idea which was proposed by Novak and colleagues in 2012, and they call it virtual ray lights. The motivation behind the whole approach is that they developed these virtual ray lights for participating media, first of all. So in participating media, we have these scenes which could be simple, which can be generated by just performing single scattering, because here you have multiple light sources and you could easily perform single scattering to get a more realistic approach, appearance. But in the scenes where you have clouds, this might not always work. For example, we saw this scene in the last lecture also. So this is the juice, orange juice, which is rendered after single scattering. You could tell by just looking at the image that it does not look kind of real. It does not look like an orange juice. But after applying multiple scattering, you could see the difference, and it kind of matches closely to what we know the orange juice looks like. Right? So the idea of using virtual ray lights was to to kind of compute multiple scattering events, which are important to get a realistic appearance there. So what we have seen so far is that all these methods which we are talking about, they comes from bidirectional path tracing. So in bidirectional path tracing, you have the light path, you have the eye path, and you connect it at a certain point. You are aware of photon mapping. The idea of photon mapping can be extended to volumetric photon mapping. We didn't talk about it, but the idea is the same. You generate photons from the light source, and just like in the surface photon mapping, where at a surface point you kind of compensate for the you kind of compute the contribution of all the photons at a particular point by doing some kind of finite gathering and blurring by the kernel estimation. You can do the same kernel estimation in the volumetric form, but this time you will do it over the full sphere visible. The problem here was that it requires a lot of photons. There was recent works by, I think Carol talked about this, about progressive photon mapping, which resolved this issue. There was another approach which we didn't talk about, but I can briefly mention that. I don't want to discuss that because that requires in itself a good set of slides to explain this properly. But I'll just tell you the idea that instead of performing photon mapping, you could also do some kind of generate beams. So what you do is that you generate the full beam instead of a photon, and you then after that you perform kernel estimation on all these beams, and thanks to that the scene could be converged faster. The only problem here is that it does not handle multiple scattering. And of course, what we are talking about from so far with the virtual point lights, it of course can be used to perform volumetric rendering. We have seen one scene where we saw those sparkling smoke, which were compensated or bounded and compensated by different approaches. This works also, but again, it's since there are issues with the singularities and loss of illumination, better things are always required. So what we will talk about in this part of the lecture is virtual ray lights, where we treat each random, so we perform this random walk and each ray is treated as a light source there, a virtual light source. Let's look at how this works. So you have the point lights, you have the corresponding ray lights. What benefits we are getting by going from point space to, let's say, the ray space here, is that you reduce the corresponding singularities which can happen. There is no need of clamping or introducing any bias, or everything stays unbiased. It can increase the sampling of the path space, which means that since you are, instead of assuming a light source from a point light, you are treating the full segment as your array as your light source, you have somehow increased your sampling. So you have increased your the area or the length of the dimension to where from the light source is coming, which means that this of course this is also helps improve the quality of the render. And at the end, this approach also helps handle better the anisotropic media, and this we will demonstrate pretty much soon. Just to give you a quick demo here how the VRLs work, the virtual ray lights. So initially you see these artifacts because of the ray lights which are visible, but after sufficient number of time, these artifacts are not visible and you could see the images rendered pretty well. Okay, so how the idea works. In the case of VPLs, we were shooting the point lights from the path, from the light source. There was a camera array and you were connecting to all of these light sources. In the case of virtual ray lights, you will treat each of the segment as a light source. And then you will connect each of these ray light, you will compute the corresponding contribution to the camera array. This, if you do it from within the medium to medium, this is termed as media to media computation. If you can also do the same computation at a particular surface, which might be inside the volume, and that's termed as media to surface computation. And you can continue this random walk and then keep computing your corresponding contributions from media to media or media to surface. Let's look at this ray-to-ray transport in a more closed manner. So you have this orange ray, which is your virtual ray light, which has a flux phi and length t. The green arrow is the green ray is the camera ray, which has a length of s, let's say. What we are doing when we compute the corresponding gradients, we are computing the contribution over both the rays, which means that we have this double integral, which is going over the camera ray and the light ray, the integral over the t here. So to understand it better, let's look at, let's make a subspace of these two rays. The horizontal axis is the camera ray axis, the vertical axis is the light ray axis. Any point in this space, this black dot represents the corresponding contribution or interaction between the ray at a particular point. So here, the U point on the camera ray and the V point on the light, on the virtual ray light. Now, one thing we can start by looking at is the phase functions at each of these two locations. So at U and V, we look at the corresponding phase, which is denoted as f of s and theta of u and theta of v. Let's assume for this illustration that the product of the phase functions at both the points u and v looks like that, where red means very high value and blue is the zero term. Blue is 0. Next, we care about the scattering, which is happening at each of the point. So you have these scattering coefficients at each of the points u and v. Given that we assume a heterogeneous medium, this could look really complicated. This is generated by Perlin noise, this particular scattering coefficient product. And in the last term is what we are interested in is the corresponding transmittance. So when you go from one point to another, there are 3 segments here, one on the U, one on the V, and one in between. And the corresponding product of this transmittance looks like that. All right, so after that, there is also a visibility term between the 2 points U and V. What it means is that if it is 0, there is no visibility, there is an occluder in that, otherwise it's visible. this is one instance of this visibility where the blue means 0, which means no visibility, and 1, which is the red term, the red color here, the magenta, the dark red is the visible portion. Now, this term also needs to be normalized with the square distance between the 2 points u and v, which you're computing. And this inverse square distance has this, this kind of form given the location of your u and v. And the overall product of all these integral, the full integrand here, looks like this. Now we want to approximate this using Monte Carlo integration. It can be computed analytically, but this would be only feasible for simple scenes where you will, we saw in the last lecture how you can simplify your all these components. If you have a constant isotropic phase function, you can simply replace it by 1/4 pi. If you have homogeneous media, you can simply assume that your sigma, the scattering coefficients, are constant, and you can also replace your phase functions by the constant by the hg function, the hg phase function itself. So, and similarly, if you have all these terms included in that, if you, let's say, don't consider visibility, this can be computed analytically, but that's not always possible. So what we want to do is we want to find a way to importance sample these different components of the integrand to improve the overall quality of rendering when we are performing rendering using, let's say, these VRLs. Let's look at the simple cases first. By simple cases is what I already described. We start with, let's say, no visibility problem. We say that everything is visible. There is no occlusion. We say that there is no heterogeneous media, which means everything is homogeneous. The transmittance is simply the exponential term of the constant term, the scattering coefficient. And you can see that on the right side how this product of these two terms is changing. I'm flipping back and forth to show you the product of these two terms, of all these terms changing when you have heterogeneous media and when you have homogeneous media. All right, we can further simplify our life and assume a constant isotropic phase function. And after all these simplifying assumptions, you see that the product, your integrand, the product of all terms, looks pretty much same as the inverse square distance term. And what it means is that you can, if, for example, if you consider one VRL in this scene and the corresponding pixel as your camera ray, then what we want to do when we want to perform the importance sampling under all those assumptions which we laid down, you want to make sure that your samples are generated in such a way that they mimic well the corresponding loop there. So what we do is that we perform that conditional and marginal PDF computation, which we have seen before. So here, just to show you again, what you do is that you marginalize your VRLs, your PDF for sampling VRLs. And once you have that, then for one particular location of your VRL, you importance sample the corresponding, use the conditional to get the corresponding sample on the camera. And that gives you the corresponding sample on the camera. By performing this operation for each of the samples, you could actually generate all the samples. But there is one slight problem here. The only problem here is that even though by simple trigonometric operations, we can write the W term, which is the distance, this dashed line, the length of the dashed line here, in this PDF, the inverse term, the term in the denominator, the double integral over, which is over the T and the S, this is not easy to compute. You can try to compute it and you would see the problem there right away. So what Novak and colleagues found that instead of computing this integral over a finite distance, you can imagine your camera ray is infinite without any loss of generality. So just by making this assumption, they managed to compute this PDF in an analytical form, which has which looks quite heavy, but it's still easy to solve, and you can perform importance sampling using this PDF. And given this PDF, they use the inverse CDF operation to generate the corresponding samples. Now, one of the point here to note here is that at a given point, they also need to compute the corresponding, they also need to perform the sampling over the angular domain. So this is very similar to the equiangular sampling, which we discussed last lecture, where we saw that you could actually perform this sampling by generating samples which are constant in the angular space, which means that they are generated as inverse of the distance square term, which means that the samples will be more concentrated where your light source is, right? Now, under all these assumptions which we put, it is, this is just few examples of the PDF generated, and you could see that these PDFs match clearly the underlying sample distribution match clearly the PDF there, which is good. Coming back to this, all the products which we are looking at, we can start removing the simplifications. Let's now consider your phase function, which could be anisotropic. In this case, if we now, you can see the integrand itself also has changed. So in the isotropic case, things were matching well. But if you have an anisotropic phase function, you could see the change in the appearance. So here, when we are talking about an isotropic phase function, we are assuming a phase forward scattering phase function here. So you could see the change in the appearance of the whole image also for the same scene. So what we want to do is we want to somehow better compute the corresponding sample density. Here you can see that the samples are not computed according to what you would observe. Since blue is the kind of a zero region and red is the high values, we would prefer the samples to be more centered around these red lobes there, right? So the idea is the same. Now we have the phase functions involved in our PDF, which is the product of these two terms. What you can assume is that if we assume as isotropic medium, what they did is that they kept the corresponding PDF in the same form, and they use the same, sorry about that, they use the same simplification of assuming an infinite camera array. And by doing that, what they perform is that they use for the given phase function. So this was equiangular sampling. So what they assume, this is equivalent to the isotropic case. But when you have an anisotropic media, which means that you have different phase function at different locations of your camera array, then they start importance sampling this phase function product depending on the way the phase function is defined. So for example, in this case, the red rays will get more weighted compared to the blue rays, depending on the product of these two phase functions at the locations shown in there, in the green lobe and in the orange lobe. You could see the change in the red and the blue rays there. Okay, so in the angular domain, if you look at, you have the phase function with respect to the BRL as the orange curve. You have the phase function with respect to the ray, the camera ray itself. What you can also do is simply is that you can say that, okay, I'm gonna importance sample with respect to the VRL, or I'm gonna importance sample with respect to the camera ray. But that could be inefficient, which we have seen when we were studying the multiple importance sampling, where the idea is the same. Either you perform importance sampling with respect to the BSDF, or you perform importance sampling with respect to the light source, because there are regions which are getting benefit from each of these samplings. It would be more efficient to actually importance sample the product here. But this could be really challenging to compute, and it could be not efficient. So what they did is that they generated just 10 samples to kind of approximate this product well. They important sample this 10 samples in such a way that they don't miss the kind of sharp features in this product itself, and they evaluate the corresponding curve of this product of the phase functions as either a linear interpolation, which it looks pretty much close to the product, or the quadratic piecewise. And in the quadratic case, I'll show you now just in the next slide how this closely matches the integral itself. Here as I said, they assume 10 adaptively distributed vertices to make sure to find a good trade-off between the speed and the quality. And here you can see that how the product is well matched. In the top, they use this linear interpolation. On the top right side, they use this quadratic interpolation. So all these things, you can see that the blue curve is well matched by the dashed curve, which is good, and it was a good trade-off instead of really looking for computing the proper important sampling of the product. All right. Now, what we have done is that we have, we have included the phase functions. Next, let's make our lives a bit more complicated and assume scattering. And once you have the scattering, which means your medium is heterogeneous, you could imagine that things could go difficult to handle. So what Novak and colleagues in this work they proposed is that they handle both of these components separately. So we have seen how the phase functions, which means the anisotropy, was handled, how the corresponding inverse of the square distance was handled, and they handle the heterogeneity separately, and they propose to MIS these two terms later on when they perform the rendering pass. So let's look at the heterogeneous term. So in the PDF, you have, if we are just considering the scattering coefficients and the corresponding transmittance, you could see you have the sigma s, t, again sigma s, and t with respect to the corresponding vertices, of course, and the transmittance of the UV term itself there. The good point is that if you, for an instant, ignore the transmittance which was happening between the curves, U and V, if you remember, these two components are separable here, because one is along the camera ray and the other is along the VRL. And what now happens is that you can actually generate each of these PDFs separately and import and sample them. And once this is generated, they perform the MIS of this PDF with respect to the PDF generated from the anisotropy over the inverse square distances. All right. So far we have discussed a lot of math here. I hope you're still with me. We have simply talked about looking at different PDFs and how to generate the corresponding important samples from that, right? Let's now look at a more simplified way to appreciate the results by all these approaches. So the first result, of course, was this nice looking fruit juice, which has this homogeneous anisotropic phase function. Once you render this with virtual ray lights, on one side, on the right side, you have the VPLs. On the left side, you have the virtual ray lights. You could see how the improvements are visible. You could see that in the VPL approach on the right side, you have these spikes, the singularities are visible there. But in the case of the corresponding virtual ray lights, there are no such singularities. So the energy is well spread. As you can see, these insets, it's kind of visible. The fireflies kind of things are visible there after 60 seconds in the case of VPLs, and even after 1200 seconds. But in the case of VRLs, this was not the case. There is this nice smoky room, which has a heterogeneous medium. And you can observe that in the VPLs, you have this sparkling effect happening under the table. In the VRLs, things are pretty much the same everywhere. VPLs kind of seems to get rid of these singularities, but they are seems to be still there. This is what happens at the scene, at the inset there after 100 seconds or so. On the one side with virtual gray lights, you could see that the medium is well rendered, smooth, whereas in the case of virtual point lights, there are so many sparkles there. And these are the singularities because of the geometric terms. All right, so this is another scene where it is the media to surface, where you have this kind of this black smoke, if you could see in the room. And when rendered, you could see that there are these specular terms. And even in the case of VRLs, you could see some specular terms on the left side. So for the media to surface interactions, they needed to handle it more carefully. They needed to clamp a little bit these things. But this was a special case for them to handle. All right, so last example here for VPL versus VRL approach is the temporal coherency. So you could see that from this animation, how the VPLs could be really distracting, whereas VRL seems to be more smooth when rendered for animating the light source. And this is when even when you put more resources, you kind of more generate more frames. So VPLs where you have 3 minutes per frame, here they still are not comparable to the VRLs. All right, so what we have seen is that we have seen two methods, VSL before and now the VRLs. In the VRLs, what we do is that we turn the segments of the paths into light sources. The advantages is that the energy spread along the lines, the singularity is kind of reduced. As well noted, it is not removed because they also have this inverse square distance term, but the singularity is remarkably reduced there. They are unbiased and temporally stable. The disadvantage, of course, in this case is also similar to the VSL. They need 2D integration along both the rays, which could be a demotivating factor. All right, so in the next part, we will now talk about LightCuts, but before I move ahead, please feel free to ask if you have any questions. All right, so if there is no question, so we talked about how to spread the energy over the um, non-Dirac regions, like the finite area regions, finite volume regions. We want to understand how well they scale. So we will not talk about these VRLs or VSLs. There are special methods developed to accelerate the VPL approaches. So we are now back to VPL approaches, the virtual point lights. We'll talk about LightCuts, how they help improve the overall speed and scalability of the method, how we can use it to render large scenes with more complicated lights without really spending all our resources. Okay, so the underlying scene is rendered with environment lighting, with the corresponding lights from the kitchen itself. There is a sun and sky light also coming from the window. On one side, you can see the shadows on the table. So all these effects all these different lighting sources are used in this scene. And this unified illumination could be really challenging if you just want to do it with fast tracing. It can happen, of course, but it could be more noisy. So this approach again was developed by like 15 years ago by Walter and colleagues, the LightCuts. The idea is really simple, but it considers all light sources. So which means that it is slow. they perform, there is another way to look at this approach, is that you can say that I can perform importance sampling, which was introduced by Shell and colleagues, where importance sampling is performed with respect to the power of the light sources, the fraction of that, which means that you weight the importance weights are the fractional power of the lights. It's this method works, but it is also too noisy. So the way the LightCuts work is that you have different light sources in your scene, and you want to shade this region. So given that you have the VPLs available, the brute force approach, the kind of the brute force approach is that you connect to all the light sources. Now, even when you try to connect to all the light sources, you need to be very careful. If there is a occlusion in your scene, you have to be careful to handle those occlusions well. So LightCuts help amortize this computation. The way it works is that you have your original lights and you create a light tree from these original lights, which kind of represents your light cluster. So once you have your light tree built, you use the same light tree, in the LightCut approach, you use the same light tree for the rest of the scene. What it means now when you want to perform a LightCut is that, let's say you want to perform a computation on one of the points, the dark circle, the black circle shown on the left box. When you perform this LightCut on the right side, which is shown by this gray line, it kind of says that you connect to the green light. If you select this cut, it means that you are connecting to both the green and the blue light. If you select this cut, it means that you're selecting the green and the yellow and the blue light. The process goes on, so you can have any kind of light cut you want in this light tree. And what it would mean is that you would connect to the corresponding lights which are present in the light cut, in the tree which you have cut so far. The way to kind of recursively stop this query for the light tree is that you either stop when you hit the corresponding leaf nodes, or when the corresponding power of the light source is with respect to your threshold is let's say low. Well, sorry, it's high. So given this kind of light cuts, you can perform your illumination. There could be any kind of light cuts. So you could take any other light cut, and depending on that light cut, you would see that the corresponding illumination at a particular point is taking care of all the lights which are on, let's say, the top side of this tree. Now, what do you think is, so do you observe some pattern in all these light cuts? Like, do you see what, since we are using the same tree which was built from the start, like there was, for each scene there's a light cut, the light tree is built and the same light tree is used, which means that the location of the lights are fixed. So do you see a problem with that? Or I should ask really, like, what do you think the problem could be with that? So if you really observe here, what's happening is that the green light, which is at the top, is always sampled, which means that some of the light sources are always given preference over another just because the way the tree is constructed, right? And this could be a problem because maybe that light is not available, is not a good way to connect to the corresponding point which I want to illuminate. We have seen different kind of scenes where the light source was in a different room and the camera was placed in a different room. So depending on, in this case, the way, whatever the light cut you choose, it appears that you will always have but some light sources which will always get improvements. The whole process requires some pre-processing where you, of course, needs to convert all the illumination to VPLs and build the light tree. And then for each ray, each camera ray, you choose a cut which approximates the illumination. And again, the issue here, as I mentioned, is that the top of the light and the top of the trees are most likely to sampled, which is a problem. Since the same lights are used in the same light tree is used for the full image, there are some sampling correlations which could be bad. And different light trees favor different lights. This is also a different issue here. Because whatever the tree you create, they will be a favor to particular lights all the time. And that's not good, whatever the light cut you choose. Okay, so what's the issue with this? What you think could happen? So this is the example of using the light cut approach. And as you can see, the flickering which is happening. This is not good. And we want to get rid of that. So there was recently, last year, there was this nice idea proposed by Cem Yuksel in HPG 2019, which was called stochastic light cuts. The idea is rather simple. So what he said is that let's assume there is no representative light. Because this is what we want to get rid of. And what he does is that he replaces each node by all the lights available under the node. So if you see at the top, in the top node, since we use 8 light sources, 8 VPLs, then the top node has all these 8 VPLs. The node in the second level has 4 lights underneath them. So they use 4 VPLs per node there, and so on. So you could see that. And this, by doing this, by representing their light tree in this form, what they do is that they randomly select the light source every time for each node. And thanks to that, they remove the corresponding correlations, which were causing the corresponding artifacts. The nice effect is that there is no flickering anymore because there were no sample correlations, thanks to the stochasticity introduced by the light tree itself. And there is no one such light which is a representative light. And here, I think the only issue is that the light sample count can be limited. Now, if we see the corresponding comparison, so yeah, this should play. So with 1400 lights, if you use 1000 VPLs, you see there is flickering with light cuts. If you have 100 VPLs, the light cuts still show issues. And with 10 light samples, you still have a lot of issues. But with stochastic light cuts, by just using 10 light samples, you see that the image is very well. I'm just going to play it again. Oops, sorry about that. So yeah, as you can see, there is no problem. There is no flickering anymore. All right, so this was a simple idea of using stochastic light cuts. I didn't go into detail because they use hierarchical importance sampling to select how different, how you select light from one node to another. That's a bit more detail, but I just wanted to give you this idea. Before we wrap up this lecture, there is another component I want to talk about. The same set of authors, Cem Yuksel and Jan Yuksel. Jan Yuksel was the first author. In 2017 SIGGRAPH, they proposed this lighting grid hierarchy, where they wanted to compute the explosions in a faster manner. So let's look at the challenges when you want to render explosions. There are animated volumetric light sources. The fire has very high variations, and the smoke, the light of the fire also creates shadows because of the heavy smoke layers. Because if there is some smoke layer which are more absorbing, which is more dark, it will create shadows with respect to the emission happening from other layers. Now the smoke illumination by the fire of the explosion has been handled in different ways in industry. So what they consider sometimes, there is either they consider there is no illumination by the smoke, by the explosion, or there are some kind of 2D filtering or happening where they simply composite the lighting due to the smoke or the explosion. And there are some 3D filtering diffusion techniques also applied. The same applies to the environmental illumination by the fire of the explosion. So again, either depending on the budget they have, they either ignore this illumination or they place few hand-placed lights to approximate the illumination in the environment. There are some inferior representation of fire volumes as light sources also. The idea which was proposed, which is called lighting grid hierarchy, the way it works is that they convert the volume to many point lights, the version point lights. They build a hierarchy, a grid hierarchy. They pre-compute the volumetric shadows in cube maps. I will not go into details in that. And they allow you to add multiple scattering if required. So they can do single scattering, and if desired, multiple scattering can also be added. And once this hierarchy is created, they simply render using this grid hierarchy. The idea is that they create this multi-resolution representation of lighting with no clustering, no binary decisions, no sharp thresholds, which helps them keep the temporal coherency. So I will show you now how this works. So this is a simple, just an overview of how this multi-resolution representation works. At level 0, you have all the VPLs, all the light sources, 900,000. Level 1, you see that it becomes coarser, and as you come to level 6, you see that there are only 50 VPLs, the coarse level, which kind of represents the full illumination of the scene here, of the smoke. So there is no trickery. What they do is that they take the volume data and they represent it as point lights. There is nothing special happening. And this is the InShot from their work. The way it works is that you, on the left side, you have the simulation grid. Let's say this is your simulation grid, where at the 0th level, each voxel center here of the smoke, let's say these voxels kind of represents the underlying smoke. The center of these voxels represent the light source, the VPLs itself. And at level 1, they place this dashed grid with coarser resolution, and they perform trilinear interpolation to place the corresponding contribution of these light sources, which are in this dashed red squares on the vertices in the 3rd level 1 grid. And once you have this trilinear interpolation done, then they compute the corresponding contribution of the light sources in each of the voxels. And this process continues to the level 2 and so on, to the depending on how many lights, how big is your volume is. And every time they kind of reduce the overall resolution by 2. So in 3D, it will be 2 by 2 by 2, which means by 8 voxels. So this is how the illumination of all these levels looks like. So at level 0, you could see the fire looks pretty much the way it should be. And as you go from level 1 to level 6, you could see that it becomes, the overall illumination becomes coarser and coarser. What they do is that in between the levels, they blend these values to have a nice smooth behavior. So they define one distance R0 and the corresponding blend function, and all the distances R1, R2, R3 are a function of the previous R0. So as written on the right side, what it means is that at level 0, you will have this red circle, and you will perform your shading from all the light VPLs which are present in the red circle. And as you go in the level 1, which is a coarser level, it kind of means that you are performing your queries among in this green circle here. And this is so on, the radius continues increasing as they go in the most coarser level, because the kind of the receptive field is increasing for each shading point there. as I mentioned earlier, they propose also to include multiple scattering if required. On the left two images, you could see that the scattering with the single scattering and multiple scattering, the difference is not visible. But if you look at the difference image, which is the luminance difference scaled by 2, the real difference happens in the more bright regions with multiple scattering. So this is the final result. So you can see that with path tracing on the left side, the image, the smoke is very noisy, but with their approach, the lighting grid hierarchy, they get a very smooth representation of the whole smoke without any problem. In the last slide of today's lecture, I'll show this nice rendering comes out of their paper, where they rendered this SIGGRAPH logo, SIGGRAPH, which is a translucent object, and all the balls are the light sources. And you can see that this rendered remarkably well, and each of the light source also kind of put shadows on each other. So they handle the shadows very well. This is really, really remarkable. Just to show you again. So with this, I will stop today's lecture